Okay, so this chapter will have easier derivatives. So all the stuff with the chain rule, we still need to know how to do it. The derivatives get much easier here. We're just going to look at applications. We won't really get to word problems until after the quiz. So when we get into 5.4, 5.5, and 5.6, that's when the real applications will come in. Okay? So the first lesson we're going to look at extreme values. Extreme values meaning just maximums and minimums. Okay? You've done a little bit of this in pre-calculus. So let's take a look at the sine curve and the cosine curve. We have what are called absolute maximums and absolute minimums, meaning like the highest point on the graph and the lowest point. Now, we're going to look specifically just between negative pi and pi for both of these. So where is the absolute maximum of the sine? Okay, yes, perfect. Okay, so when I have maximums, I would like you to write f of pi over 2 equals 1. The reason being, this is the maximum value, and this is where it occurs. So I prefer the function notation over the just ordered pair, okay? And I don't want you to just tell me the y value. If you rate the ordered pair, I'll give you credit. I'm just on quizzes and tests, I usually will write it in this form. Okay, so here's absolute maximum. And absolute minimum will be down here. Oh, I wrote F. This is supposed to be G. Sorry about that. This is G of X. So the minimum will be G of negative pi over 2 equals negative 1. Okay, this one is F of X. F of X, okay, so cosine of X, we have an absolute maximum at 0, and that has a value of 1. But what's happening with the absolute minimum?
There's 2.
Okay, there's 2 locations on this graph. Now, both of these are going to be the same value. So f of negative pi is the same as f of pi, which equals 0. So these are the minimum. So we say the minimum, I meant to write that. Sorry. Negative 1. So the minimum is the same, the absolute minimum is the same value, but it just occurs at 2 different locations. Now imagine if this was from negative infinity to infinity, all our maximum and minimum values would be the same. They would just occur at, right, odd multiples of pi over 2, right, for that, here, multiples of pi.
That's the notation you want to write in.
Yeah, so you'll see when we do on the next one. Let's look at the absolute extrema of f of x equals x squared. We got a parabola. And I'm just going to change the domain so we can determine our absolute maximum and minimum. Okay, if it goes from negative infinity to infinity, is there an absolute maximum? No. So we're not going to write infinity. We're just going to say none, right? Do we have an absolute minimum?
Yes, we do.
Yeah, that's going to be the vertex. So that's f of 0 equals 0. Now, what if we restrict it from 0 to 2? So just looking at 0 to 2, what's our absolute maximum? F of 2 equals 4. And our absolute minimum, f of 0 equals 0. So in this case, we have clear endpoints. What if I now changed it to parentheses 0 to 2? So almost like, think if you have an open circle to a closed circle. Okay, well, our absolute maximum, it's still going to be the same, right? F of 2 equals 4. What about the minimum?
Limit?
Okay, so a minimum must be an actual point. It can't be a limit. It's not like an asymptote, okay? It can get closer and closer and closer to zero, but will it ever reach zero? So we're going to say none. So by changing one of the endpoints to not include, right, took away that. So what do you think is going to happen if I make both of them? Both are going to be none. Okay, so there's one clear thing I want you to take away from this, and that is which one had both a maximum and a minimum? The one that had the closed interval. Yeah.
Would the absolute minimum maximum not just be like as close as you can get to zero?
But it has to be an actual point.
Got it.
So is there an actual point
That
when, like, okay, so you could say, oh, my minimum is 0.0001. Well, can you find something smaller and something smaller? Okay, so it is, you think of it as a limit, which it actually is. If I said, what's the limit as x approaches zero from the right, you'd say that's equal to zero. But that's a limit. It's not an actual point. Okay? So that leads us into our extreme value theorem. Okay, there are 4 major theorems that you need to know for the class and for the AP exam. One we've already done. That was intermediate value theorem. That was IVT. That basically says if you have a point like down here and up here on a continuous function, has to take on all the y values in between. This one, okay, we need to have a continuous function on a closed interval. Okay, then f must have both a maximum value and a minimum value. Okay, so for example, the only one that had a closed interval was the only one that had an absolute maximum and absolute minimum. So that ensured it. So all these others, we're not going to necessarily have both. Okay, what I'm going to do, we're going to have steps and then we'll walk through the example on the next page. So to find the maximum, and this is absolute, okay, step 1, we're going to find what's called critical points. A critical point, this is a point that's in the domain where f prime equals 0 or does not exist. Okay, let's think about that. Where does f prime equal 0? What occurs there?
Horizontal tangent.
Horizontal tangent, okay? So imagine here, this would be a horizontal tangent. So that would look like, you know, like a parabola or something where we have a horizontal tangent. That's going to be a maximum or a minimum. And where does f prime not exist? Cusp, corner, vertical tangent. Okay. Now remember, critical points have to be in the domain, so there has to be a continuity there. Right? So it's got to be on a continuous. Yeah. So just keep in mind, the only situation we have here, this would be a corner, cusp, or a vertical tangent. Okay. So if you think like a corner, a cusp, right? Those would be, like that could be a minimum, that could be a minimum. Okay, then the next step, we'll refer back to this. We're going to evaluate f of x at each critical point and both endpoints. And then just figure out what's the largest. That's our absolute maximum. Smallest, absolute minimum. So absolute maximums could occur at a critical point or at an endpoint. So here's just a bunch of pictures just kind of demonstrating. Like here, the absolute maximums at a critical point, absolute minimums at a critical point. Here, the absolute maximums at an endpoint. Okay, so here we don't have any critical points. So the endpoints would be the absolute extreme. Here, there's an absolute min here, absolute max here, min, absolute
What
max.
about the relative? What about
We'll do that later. Okay? We're just doing absolute first.
To get my stuff.
Okay, that's fine. I'm recording it anyway, Lily, so. Okay, let's tackle this. These are fun. Okay. Now, I know you can do this with pre-calculus, but we are going to do this with calculus. This is a parabola. Okay, so you should be able to tell where our maximum or minimum would be by finding the vertex. Okay, but I don't want you to do it that way. We are going to follow the steps from the previous page. Okay, so I want you to establish, they gave us a domain. First of all, they gave us a closed interval. So we know there's going to be an absolute maximum and an absolute minimum. So step one, if I go back here, got to find the critical points. So I'm going to take the derivative. So step one, we're going to do f prime. Okay, that's going to be negative 2x plus 4. Much easier than the ones you just did on your test. Now, I want to see where this is equal to 0 or where it's undefined. It's not undefined anywhere, so we're just going to set this equal to 0. Okay, so this is all part of step one. All of step one is find the critical points. And then, oh, just a quick note, we always want to make sure the critical points are in the domain. So we're going to set f prime of x equal to 0 or see where it does not exist. So I'm setting f prime equal to 0. And what do we get for x? 2. Okay, double check. Yes, that's between our 0 and 3. So this is a critical point. Okay, step one is done. We have one critical point, which hopefully makes sense. It's a parabola. It's an upside down parabola. So we should only have one place where there's a horizontal tangent. Okay, next, step two. We're going to evaluate f of x at each critical point and both endpoints. So, okay, we're going to take this original function and we're going to plug in f of 2, f of 0, and f of 3. So the derivatives was to find the critical point. Now we go back and plug it in because we want to see what's the actual largest and smallest value. Okay, we can do this, right? Let's see. Negative 4 plus 8 minus 5 gives us...
you plug it back in the original?
Yeah. Notice here I put f. Remember how I said I like that function notation for a reason instead of using an ordered pair? So I remember also what am I plugging into? I'm plugging into f of x. I'm not plugging into the derivative. Okay, plugging in 0 is easy. That's negative 5. And plug in 3, that'll be negative 9. Plus 12 minus 5 gives us... Yeah. Okay, what's our absolute maximum value? And what's our absolute minimum value? F of 2 equals negative 1. That negative 1 is the biggest y value. And what's our smallest y value? F of 0 equals negative 5. Beautiful. No. Whoa. All right, first thing. F prime of x. Now, some of you might be looking, or maybe not, x to the 2/3, even over odd. It's a cusp. Okay. But I want to just make sure, let's confirm that. Listen, even if you didn't recognize that it's a cusp, if you follow the steps, you'll still end up with the same result for our critical points. Okay, that's going to be 2/3 x to the negative 1/3. Okay, I'm just going to rewrite this. So if it's 2 over 3 cube root of x. Okay, now I want to check for two things. I want to check, is f prime of x equal to 0? Or is f prime of x undefined? Okay, well, when I have a rational function, okay, when I'm looking for where the derivative is equal to 0, I just set the numerator equal to 0. But that's not possible, right? 2 can't be equal to 0. Okay, so there's no place where the derivative will be equal to 0. What about undefined? I set the denominator equal to 0. right? Which is just going to give me x equals 0. Right? Divide both sides by 3, cube both sides. You didn't need to show any of that work. Is that in the domain that I was provided? Yep, that's a critical point. So far, okay. So again, derivative, see where it's equal to 0. This one isn't. See where it's undefined, we got 0. Now, next step, we're going to take our original function and we're going to plug in 0 and -2 and 3. So I am going to write f of 0, f of -2, and f of 3. Now keep in mind, x to the 2/3. How can I write x to the 2/3? That would be cube root x squared. Okay. So cube root of 0 squared, well, that's just going to be 0. Cube root of -2 squared is just going to be cube root of 4. Cube root of 3 squared is going to be cube root of 9. So I don't need you to actually get the decimal approximation, but you should be able to tell which one's bigger and which one's smaller, right?
I think so.
Okay. So we have an absolute maximum. We have an absolute minimum. Where's our absolute maximum?
Wait.
Minimum. That would be our minimum.
Wait. I know that's what I thought.
Oh, did I say it backwards from how you thought I was going to say it?
I don't know.
All right, f of 0 equals 0. And then clearly cube root of 9 is going to be bigger than cube root of 4. Clearly. So f of 3. Oh, okay. So listen, if it's a cube root, whatever's under the radical, if that one's bigger, yeah, I'm not comparing a cube root to a fourth root with different numbers. It's a cube root to a cube root. Of course. Okay. Questions so far? All right, let's do one more of these. What? Right, f prime. Okay, that's going to be e to the negative x times -1. So my derivative is -1 over e to the x. Okay, checking my critical points. So remember what I said on the previous one. If I'm checking where f prime of x equals 0, not possible, right? I can't set -1 equal to 0. So that's not going to work. Or where is f prime undefined? Okay, well, I could try to set e to the x equals 0 and solve it. But that, okay, so first of all, okay, I could do natural log. And I would get natural log of 0, but that's a problem because we can't take the natural log of 0. That's not in the domain. So that means there are no critical points. Okay, now that's fine. Okay, that just means we're only going to have to plug in the endpoints. Okay, e to the negative x. If you think about e to the negative x, that's an exponential decay, right? So if I have this and I restrict it from -1 to +1, it only makes sense that the endpoints would be the absolute maximum. So let's see, f of -1. Well, what will that give us? Just e. And f of 1 would give 1 over e. Okay, so this is our absolute maximum. And here's our absolute minimum. I told you this was fun, right? This is a fun lesson. Okay. Okay, somebody asked, who was it? Somebody asked about relative. Oh, sorry. You did. Okay, we're getting there. We're doing the relative next. It's okay. I have time. There's just a lot of words in this. There's a reason that.
Where we don't have it.
But that's like the worst day not to have it. What? Lit. We have it every single day. No, we don't have
bad.
Fridays. Friday doesn't count. I wish I had it on
Okay.
Yeah.
Okay, local or relative extreme values. So, extreme value theorem tells us about the largest and the smallest. Okay, but that doesn't mean that there aren't other places where we have terms in the graph, right? We have local or relative, so just make sure you know both terminology. So if I ask you for local or relative, they're the same. Local, sometimes you hear the words local, like that just means within a smaller interval, right? And sometimes you hear relative meaning, again, within relation to that smaller part of the graph.
I just thought it's like whatever's north of
Yeah.
Oh,
like a relative.
yeah.
No, I didn't think about it.
Okay, so here's the thing. You can have, like, your local and relative can be any extreme values. Your absolute are just the biggest and the smallest of them. Okay. This is just how we describe it. Again, you just always want to make sure that when we're doing this, because we're still going to be working with critical points, it's still in the domain. Let's just move on to the next page where I have the steps written out. Okay. And you know what I'm going to do? There's an example at the bottom of the page, so we'll go through steps as we do the example. Previously, the domain was always given. With these problems, the domain is not always listed, so that's going to be our step one. So I'm going to jump down here. This is just a polynomial function, so that means what is our domain? All real. So I'm just going to make a note. Okay. I always want you to do this because sometimes the domain is not going to be all reals, or it's not, like if you look at the next page, we're going to have to find a domain. Okay. Step 2. Okay, this is the same as previous. Find the critical points. Again, make sure the critical points are in the domain. So f prime of x, 6x squared plus 6x minus 12. You know what? I am literally just going to write min and that.
You know what? Because for the other one, you did abs.
Yeah. So I'm not going to worry about writing the word local or relative in front. If you want to, fine. So I'm going to assume anytime you write min, okay, it's just a relative or a local. But when you put the word absolute or abbreviate, then that notes. Does that make sense? Okay. All right. I am going to factor out a 6. That'll make it easier to factor my quadratic into x minus 2, x plus 1. Okay, I'm going to set that equal to 0. Thank you. Yep, I got it switched. Yeah, thank you. Yeah, I got it. Okay.
I make more.
Okay, we're going to set this equal to 0. Well, the 6 has no impact on that, right? We can divide both sides by 6. So I have 2 critical points. I have x equals -2 and +1. There's no denominator. There's no place where this is going to be undefined. Okay, step 3. Step 3. I'm going to create a number line for f prime of x. We're going to label any critical points and any endpoints.
What about the f of x?
Nah.
Wait, why aren't we? I know this. Sorry.
Okay. Okay, question, Lily?
Why aren't we just like doing how we plugged it in before?
Okay, so this is a cubic function. I'm not asking for in this problem, do you remember what cubic?
Yeah.
Is there going to be an absolute maximum or minimum in a cubic function? No. It goes, right? It's going to go like this.
So for this, we're not gonna.
So I'm looking for any extreme values. I'm not going to have I can't have an absolute maximum or minimum Because I don't have a closed interval.
But what I'm saying is like you don't have to plug it in calculus to add like f of -2.
Not yet.
Oh.
Okay. We're doing step 3 now. Okay, I want you to make a number line. Leave a little bit of space, like above the number line. So I'm going to put that like here. And this, I'm going to label it F prime. It's really important to label F prime versus F versus second derivative later. Okay, I want to place on there my critical points. So -2 and 1. And it's going to go from negative infinity to infinity. You don't have to put this on here. I just like to because when we write our interval notation, just a little reminder. Okay. So using the number line, we are going to test values in each interval. Remember how I labeled my number line? I put F prime for a reason because I'm plugging into F prime. We're going to label the number line with pluses and minuses where they're positive and negative. Okay, I like to plug it into the factored form. So let's say I plug in -3. So that'll be, don't worry about the 6, that's not going to affect it. Negative times negative makes it positive. Pick 0 is easiest. Positive times negative. Negative. Pick something bigger than 1. Positive times positive. Okay. Now I'd like to draw some arrows here. When F prime is positive, that means the graph is increasing. It has a positive slope. So I'm going to draw a little arrow here up to the right for that interval. F prime is negative here. That means it has a negative slope. So it's going to go decreasing. And lastly, it's going to finish off with increasing. So the arrows really mimic what the graph actually looks like. So what did I just tell us the next cube looks like? Comes here, here. That means right at the top where it switches, there is a maximum. At the bottom, there is a minimum. These are our relative maximums and minimums. Okay? Wow. Now, I'm not done because I need to know where.
Why did you do the number line?
For fun.
I mean, it was fun, but it wasn't just for fun. I want to see where F prime, what's F prime? F prime is slope. So I need to know when the slope is going from positive to negative. That's going to be a maximum. When the derivative goes from negative to positive, that's going to be a minimum. Remember, these are slopes. These are our derivatives. And the nice thing about the derivative graph is it mimics the behavior of the original graph. Is that okay? Okay, what is my maximum? It's going to be f of -2. What's my minimum? It's going to be f of 1. Again, you don't have to put the word relative or local in front. It's only necessary when it's absolute. Okay, f of -2. Oh, we can do this here. Let's see. 2 times -8, -16, plus 12. Got it. Plus 24. Got it. Plus 1. 21.
Wow.
Yay. Okay. F of 1. Oh, this one's easier. 2 plus 3, 5. Minus 12.
-7.
Plus 1. Excellent. Okay. Running close on time.
I have a very important question to ask you.
Okay. Yeah, let's do this one. I think we could do this. Okay. Domain. All right, first thing, I noticed there's a square root. So whatever's under the square root has to be greater than 0, but because it's also in the denominator, square root greater than or equal to 0, but because it's, it's going to be plus or minus 2. So if I were to just do a quick number line here, my domain is just going to be values between -2 and 2. Because if I were to factor this, kind of like what we just did, but on a smaller.
Can't it be inclusive?
No, because it's in the denominator. Okay, it can't be equal to 2 because that would make it undefined. Okay, so that's my domain. I just want to keep that in mind. And now let's do the derivative. So I'm going to keep this with a negative. I'm going to do negative 1/2. So negative 1/2, 4 minus x squared to the negative 3/2. Don't forget chain rule. Bless you. Don't forget the times negative 2x. Okay, the half and the negative 1/2 and the 2 will cancel. So I have x over 4 minus x squared to the 3/2. Okay, I want to see where f prime is equal to 0 and where it's undefined. Okay. Sure. Okay, so where is f prime of x equal to 0? When x equals 0. That's a critical point because it's in my domain. If I set the denominator equal to 0, I'll get plus or minus 2, but these are not critical points. Why? They don't exist in the domain. Okay, so critical points must be in the domain. So I'm going to make a number line with f prime. I'm going to put negative 2 and 2 here. And I just have a critical point at 0. So I like to just put the parentheses again for interval notation. Okay, remember, I labeled that as f prime, so I'm plugging that in here. Now the denominator is always going to be positive. Do you agree with that? Yeah? Okay, so it's really just plugging into the numerator. So negative 1, I get negative, positive, negative, positive, it decreases, then increases.
Is it like
No,
different?
I really
Is it
don't.
really
We don't need
different?
to.
Sort of.
I would love to say. Well, it's just 0.
No, plug it into the original.
Oh, the original.
1/2.
There you go.